Hello everyone, and thank you for watching this presentation. Today, I'm excited to introduce our work, LVLM Layer-Wise Vision Injection with Disentangled Attention, a simple yet effective approach to making large vision language models more efficient without sacrificing their performance. Recent LVLMs achieve remarkable multimodal understanding, but they remain difficult to deploy efficiently. The main reason lies in the quadratic complexity of self-attention, where computation grows rapidly with sequence length. Images typically contribute hundreds of visual tokens. For instance, outputs around 728 tokens per image, whereas the text sequence is much shorter, about 60 tokens in a typical text-TV QA example. Propagating these long visual sequences through every decoder layer drastically increases flops, delays the first generated token, and raises memory consumption. Our analysis shows that much of this visual propagation is redundant, and addressing this inefficiency forms the starting point of our work. A common direction is to prune or compress visual tokens, either before they reach the LLM or at certain decoder layers. However, these approaches often depend on manual design choices like where to exit early or how many tokens to retain. If you prune too much or too early, you lose visual details and hurt accuracy. If you prune too little, the compute savings are modest. In practice, these methods struggle to deliver large efficiency gains without compromising capability. Our approach, LVLM, disentangles how vision and language interact inside the decoder. Only the language sequence is fully propagated. The vision sequence participates through attention as keys and values, and crucially, we inject it at every layer. This replaces one large, expensive visual language interaction with multiple lightweight ones, keeping visual cues accessible without propagating all visual tokens through FFNs. The resulting complexity removes the quadratic dependence on the full multimodal length in attention and cuts FFN work to text only. Empirically, across 1B to 7B decoders, we reduce decoder flops by roughly 88 to 91%, speed up TTFT by about 2 to 4 times, and lower memory usage while maintaining comparable accuracy over a suite of benchmarks. In each decoder layer, we separate how vision and language are handled. The vision sequence is projected to keys and values using WK_V and WV_V. The language sequence is projected to queries, keys, and values using WQ_L, WK_L, WV_L. We then concatenate the vision and language key value matrices and compute attention only from the language queries. This keeps the fusion lightweight. We add positional embeddings to the language query and key, because visual tokens already carry positional cues from the vision encoder. Finally, we apply a partial causal mask. Language tokens can look back to earlier visual tokens, while language-to-language attention remains causal. Once we disentangle attention, visual tokens are no longer pushed through FFNs. If we fuse only at one layer, we risk losing rich visual cues. So we inject vision keys and values at every decoder layer. Practically, we reuse the existing LVLM connector and introduce projection matrices to align dimensions. Algorithm 1 shows the loop for each layer. We project language and vision separately, add positional embeddings to language, concatenate the key value sets, run attention from language queries, and then pass the language sequence through the FFN. This preserves visual accessibility across depth, without expensive visual FFN propagation. Computationally, the attention cost becomes linear in the total keys and linear in the number of language queries, and the FFN only processes language tokens. Formally, the total is ON 加 M 括回 MD 加 O8 MD 2括回. This removes the quadratic dependence over the full multimodal sequence that hurts vanilla models, giving us clear wins when the visual sequence is long. We evaluate LVIDA on 4 decoder scales from TNILAM 1.1b up to Vicuña 7b Lzing Sigalai SOIT 400M-14, which outputs a 728 token visual sequence per image. We report 9 standard multimodal benchmarks and efficiency metrics, including flops, TTFT, and peak memory. Training follows ELOVA data recipes. Smaller decoders use Lava 1.5 to 558K, 665K, with frozen vision encoders, while the 7B model uses lava-only vision stage 1.5 and stage 2 SI. This table gives a comprehensive comparison between LVIDA and baseline LVLMs across 4 decoder scales. Let's first look at efficiency. LVIDA consistently cuts decoder flops by around 90%. Correspondingly, the time to first token is reduced by 2 to 4 times, and peak memory usage drops by 3 to 7 gigabytes, depending on the model size. What's more important is that this efficiency gain does not compromise accuracy. Across 9 benchmarks, LVIDAS scores remain on par with or even slightly better than the baselines. We also vary the language length while keeping the vision sequence fixed. On both ends, short or long text, LVIDA maintains clear wins in FLOPs and TTFT. The advantage is especially pronounced when vision tokens dominate, which is typical for high-resolution images. This slide summarizes how LVIDA compares with existing multimodal models and token compression strategies. Looking at Table 3, using the same Vicuna 7B backbone, LVIDA reaches accuracy on par with or even slightly above leading LVLMs such as Lava 1.5 Siglip. Table 4 dives deeper into efficiency accuracy trade-offs under a consistent framework. When compared with compression-based approaches like FastV or V, LVIDA achieves over 90% FLOPs reduction while preserving task accuracy. Competing methods either reduce fewer FLOPs or suffer accuracy drops of several points. To conclude, LVIDA addresses the core inefficiency of current vision language models. In traditional LVLMs, long visual sequences are fully propagated through every decoder layer, causing redundant computation and slow inference. Our approach, layer-wise vision injection with disentangled attention, removes this bottleneck by decoupling vision and language streams and re-injecting vision keys and values at each layer without visual feed-forward propagation. As a result, LVIDA reduces decoder flops by roughly 90%, accelerates the time to first token by 2 to 4 times, and lowers memory consumption, all while maintaining accuracy on diverse benchmarks. Overall, LVIDA provides a more efficient and scalable architecture for multimodal applications, and we hope it can inspire future extensions to long context, video, and streaming perception scenarios. Thank you for your attention.